Hi, and welcome to the 9th tutorial video. This video introduces Newton's second law for rotating bodies. The first problem states, the assembly has mass ma and is hoisted using the boom and pulley system. If the winch at B draws in the cable with acceleration a, determine the compressive force in the hydraulic cylinder needed to support the boom. The boom has mass mb and mass center at G. Let's start this problem by drawing out the free body diagram for the suspended mass. There are two forces acting on it, gravity and tension. Because of the pulley system, the tension has a value of 2t, and the acceleration is a over 2. From this free body diagram, we can sum the forces in the y direction to find the tension in the cable. Now we can draw a free body diagram for the boom, and I'll start with the easiest ones. There's the force due to gravity, of course. Next, let's consider the forces from tension. The force of tension acts at the tip of the boom. For each section of cable touching the boom, you should draw a force of tension that is oriented along each cable. That means we should draw one force of tension traveling parallel to the boom for the cable that travels from the tip to the winch, and a force of 2t directly down from the tip, which supports the suspended mass. Next, we have to talk about hinges. There's a hinge at the base of the boom. Hinges can support forces in the x and y directions, but they cannot support moments. We don't know exactly what these x and y forces are at the base hinge, so we'll leave them as variables right now. Finally, we have the force from the hydraulic cylinder. With rigid links like this, we should check if two conditions are true. The first condition is whether the link is in equilibrium, meaning the forces are balanced and it's not accelerating. This hydraulic cylinder is clearly not accelerating, so it meets the first condition. The second condition is whether the link only has two hinges and no other forces acting on it. The second condition is also true for this hydraulic cylinder. Since both conditions are true, then we can say that the force acting on point C must be parallel to the hydraulic cylinder. This is a sort of shortcut, but you can get the same result by drawing a separate free body diagram for the hydraulic cylinder. Now we can sum the moments acting on the boom, and we know that the moments must sum to 0 since the boom is in equilibrium. For systems that are in equilibrium, you can sum the moments from any point. However, you can make life easier by picking a point which removes as many forces as possible from the equation. We should pick point A, since doing so causes the hinge forces at A to have no moment arm. The tension force T directed along the boom will also be removed from the equation for the same reason. We can sum the torques by multiplying each force by its moment arm, and I will take counterclockwise as the positive direction. Finally, we find that the force in the hydraulic cylinder is 289 kilonewtons. The second problem states, the truck carries the spool which has weight W and radius of gyration kg. Determine the angular acceleration of the spool if it is not tied down on the truck and the truck begins to accelerate at the rate AAT. The coefficients of static and kinetic friction between the spool and the truck bed are μs and μk respectively. I'll consider this problem as a ball on top of a block, where the block is pulled sideways. To tackle this problem, we should at first assume that the ball is in pure rolling. We can then find the friction force which would be necessary to sustain pure rolling, and check if it exceeds the maximum possible static friction force. If it doesn't, then the assumption of pure rolling is correct. If it does exceed the maximum possible static friction force, then we can replace the friction force with kinetic friction and resolve the acceleration values. We can start by drawing a free body diagram for the ball, which tells us that the normal contact force is 900 newtons. We can also apply Newton's second law in the horizontal direction, which gives us equation number 1. Next, we will apply Newton's second law for rotations. This is where you have to be careful when you choose the reference point for torques. Since this body is not in equilibrium, we don't have a choice of where to sum the moments. We must sum the moments about the point of symmetry of this object, which is in the middle. Doing so gives us equation 2. The moment of inertia can be calculated as the mass times the radius of gyration squared. The radius of gyration is the distance where, if you were to concentrate the entire mass of the object as a point mass, it would have the same moment of inertia relative to the reference point. Once you have applied Newton's second law in both the horizontal, vertical, and rotational directions, check to see if you have enough equations to solve the problem. In this case, we don't. That's a hint that we need some more relationships between the unknown variables. In this case, the accelerations of point G and point A can be related using our relative acceleration equation, which gives us equation 3. Now we have 3 equations and 3 unknowns. We can find that the force of friction here is 42.4 newtons, which is below the maximum static friction. Therefore, the assumption of pure rolling was correct. Lastly, we have problem 3. It states, the spool has mass m and radius of gyration kg. It rests on the surface of a conveyor belt for which the coefficient of static friction is μs. Determine the greatest acceleration of the conveyor so that the spool will not slip. Also, what are the initial tension in the wire and the angular acceleration of the spool? The spool is originally at rest. This problem might be a little hard to visualize, so I made this animation to show what's happening. It looks very strange, but as the conveyor moves leftward, the spool starts to move to the right. I'll play this a few more times. As always, we can start by drawing a free body diagram. I will also label the accelerations acting on both the conveyor contact point and the center of mass. Next, we apply Newton's second law. The vertical direction is straightforward. For the horizontal direction, we can recognize that the spool is on the verge of slipping, so we should use the maximum force of static friction. Newton's second law in the rotational direction, like before, must be applied about the point of symmetry of this object. Since the object is rotating clockwise, I will take clockwise as positive. Just like the last problem, we can also write a relationship between AX and AC. I'm going to write negative AC since I will take rightwards as positive for this equation. We still need one more equation to solve for the 4 unknown variables. To move forward, let's think about this point here, where the string meets the spool. I'll replay the animation, and I want you to focus on the inner ring of the spool. While this spool is moving, the point of contact between the spool and the string has an instantaneous velocity of 0, just like the point of rolling for a simple rolling object. This means that this point has 0 horizontal acceleration, so we can use that as a reference point to kind of anchor the horizontal accelerations. Equation 4 takes this into account. It's again the same relative acceleration equation that we've been working with for many tutorials now, relating the acceleration of the string contact point to the center of mass. Now we have enough equations to solve for all the variables, so just work through the math to get the answer. That's it for today's video. As always, you can contact me at this email address if you have any comments or questions. Thanks for watching, and I'll see you in the next video.